In this video, I'll present material on laboratory compaction of soils. The objectives are that you should be able to describe the laboratory compaction tests that are used. And second, you should be able to develop a laboratory compaction curve. And third, you should be able to determine the relative compaction of a soil in the field. The laboratory compaction test that is generally performed for compacting soils is the Proctor test. There are two versions. There's the standard Proctor, which is ASTM D698, and there's also a modified Proctor, which is designated as ASTM D1557. This picture shows the equipment that's used for the test. You can see that there's a mold. That's where we place the soil inside that mold and compact it in there, and then we compact it using a hammer. You can see there are two different hammers here. The shorter hammer is used for the standard Proctor, and the taller hammer, which the green line is pointing to, is used for the modified Proctor. So the standard Proctor consists of compacting soil in the mold, and that mold has a volume of 1/30th of a cubic foot, or 9.44 times 10 to the negative 4 cubic meters. We compact the soil in that mold in 3 layers of equal thickness. We compact it with 25 blows of the hammer for each layer. That hammer weighs 5.5 pounds, and it's dropped the distance, the weight is dropped a distance of 12 inches to compact the soil. The modified Proctor similarly uses a mold that has a volume of 1/30th of a cubic foot. Differences are that we will use 5 layers. We'll compact the soil in 5 layers and 25 blows of the hammer per layer. Now the hammer weighs 10 pounds. The weight of the hammer is 10 pounds, and the weight is dropped a distance of 18 inches to compact the soil. So there's more energy being used to compact the soil with the modified Proctor, which is generally considered to have energy more consistent with modern compaction equipment. After completing a series of tests in the lab, the results that we want to obtain are the moisture content for each test that we perform. We'll generally do 4 to 5 tests in the lab with different varying amounts of moisture in the soil. So we might have moisture contents vary between 7 to 13% for standard Proctor. And then each one of these molds, the soil is compacted, and there's going to be an associated dry unit weight with that. We'll take these results and we'll plot them. So we'll have the moisture content on the horizontal axis, and then we will we'll put the dry unit weight on the vertical axis. So as we get the axes labeled, following that we will then place each data point on the graph. So the first point, moisture content of 7% and a unit weight of 110 pounds per cubic foot. The second, third, and fourth points are being plotted. Then we're going to draw a curve through these data points. The peak of the curve, the highest point of the curve, is going to be the maximum dry unit weight, and the moisture content associated with that maximum dry unit weight is the optimum moisture content. So I'm designating those now. Again, maximum dry unit weight and optimum moisture content, and these are the key pieces of information that we want to obtain from the Proctor test. We will then use this maximum dry unit weight and optimum moisture content in the field to determine the relative compaction, and also then determine if we are meeting construction specifications for compacting soil. When we're compacting soil in the field, we will want to determine what the relative compaction is of the soil that's being compacted. We determine that as the dry unit weight of the soil that's being compacted in the field divided by the maximum dry unit weight that we obtained from our Proctor test. And then we will develop some construction specifications where earthwork is involved. Those construction specifications will specify the relative compaction that's required. And we need to do that for a specific test. The relative compaction will be specific to either a standard Proctor test or a modified Proctor test. We'll also provide specifications on the moisture content of the soil. So an example construction specification for compacting soil could consist of stating that the soil needs to be compacted to 90% relative compaction in accordance with ASTM D1557, which means that the modified Proctor test was used. Then we would also could specify that the moisture content must be within plus or minus 2% of the optimum moisture content. So this is one example of a construction specification for soil compaction. Now let's look at an example problem. We've conducted the Proctor test in the lab. We've obtained some data from that, and we want to then obtain the results from that data. So the data shows the mold, volume, and the results from each of the tests. We performed 5 tests. Calculations that we want to perform for each of these data points is to determine the mass of the water. So that's row C minus row D. We want to get the mass of the solids. So we'll take the value from row D minus the value from row B. We then will calculate the moisture content for that data point. So that will be our mass of water divided by the mass of solids times 100. We then want to obtain the mass of the soil that's in the mold. So we'll take the mass of the soil plus the mold in row A minus the mass of the mold. And then we want to get the mass density. So we'll take that total mass and we'll divide it by the volume of the mold, the total volume. With the mass density, we can use that to obtain the unit weight of the soil in the mold. And that's going to be equal to the mass density times gravity. And then we can then finally obtain the dry unit weight, which will be equal to our total unit weight divided by 1 plus the moisture content. So now going back and with the data that we have, we'll go ahead and perform our calculations for that first data point. So we'll start off by calculating the moisture content. The moisture content is 240.85 grams minus 231.32 grams. So we get 9.53 grams for the mass of the water. Mass of the solids, again row D minus row B, so we have the 231.32 grams, which is the mass, dry mass, minus 20.11 grams for the mass of the can. So we get 211.21 grams for the mass of solids. We divide the mass of water, take the mass of water, divide it by the mass of solids to get the moisture content of 4.5%. Mass of the soil in the mold is 3.762 kilograms minus the mass of the mold, 2.031 kilograms. So we get 1.731 kilograms. So then our mass density is that 1.731 kilograms divided by the volume of the mold. We end up with 1,833.7 kilograms per cubic meter. And we'll take that mass, divide it by mass density, and multiply it by acceleration of gravity to obtain a total unit weight of 17.99 kilonewtons per cubic meter. And then we'll take that total unit weight divided by 1 plus the moisture content of 4.5% to get a dry unit weight of 17.21 kilonewtons per cubic meter. And then I'm just highlighting the two key pieces of information that we're taking that's going to go into our plot. So this is going to provide us with one data point in our plot of dry unit weight versus moisture content that we'll then use to obtain the maximum dry unit weight and optimum moisture content. If we go ahead and perform these calculations for each data point, we can see the results in this table. So in the third row, we have all our moisture contents, and then in the last row, we have all our dry unit weights. So we just repeated those same calculations we just went over for each one of our data points. You should go ahead and repeat those calculations for one or two of these data points. This plot now shows the data points from our lab compaction test with the blue points on the plot. And I've drawn in the curve through those data points. And I'll talk about the red curve in just a minute. After having drawn in the curve, we find the peak and use that peak then to determine what the maximum dry unit weight is and the optimum moisture content. So as I look at the values on the plot, looks like the maximum dry unit weight is 19.05 kilonewtons per cubic meter, and the optimum moisture content is 11.5%. So the red curve, which is drawn in here, is designated as the zero air voids curve. That is the dry unit weight versus moisture content for the soil if the voids were completely saturated. We draw this curve in. One thing that this curve helps us is to make sure that our lab results are appropriate. If the compaction curve were to be plotted to the right of the zero air voids curve, we would know that there's something either wrong with our test results or we made an incorrect assumption with our specific gravity for the solids. And so that's one thing that the zero air voids curves helps us do on the compaction curve.